How do these interaction forces affect the rate constant of the reaction? Scatchard and Hildebrand studied these interaction forces, or cohesive energies, and arrived at a relationship for neutral molecules only. Thus, RT natural log of F2 is equal to V2 phi 1 squared, open bracket again, capital delta E2 over V2, close bracket, to the 1/2, minus, open bracket, delta E1 over V1, close bracket, to the 1/2, all to the 2. Let's call that equation 1. Here 1 represents solvent and 2 represents solute. Reference again here is Scatchard G, Chemical Review, 1931, Volume 8, page 321. Also Scatchard G, Chemical Review, 1932, Volume 10, page 229. Let's look at the parameters now. F2 is the activity coefficient of the solute referred to pure liquid state of the pure solute, while V2 is the molar volume of solute, V1 is the molar volume of the solvent, phi 1 is the volume fraction of the solvent, equal to unit for a dilute solution. Capital delta E1 is the molar energy of vaporization of the solvent as pure liquid, and this depends on van der Waals forces because we are dealing with neutral molecules here. Delta E2 is the molar energy of vaporization of the solute as pure liquid, similarly. For a dilute solution, phi 1 squared is equal to 1. Hence, the equation now becomes RT natural log of F2 is equal to V2 into, open bracket, delta E2 over V2, close to the 1/2, minus delta E1 over V1, close to the 1/2, all squared. It's Roman 2. If we put delta is equal to capital delta E2 over V2 to the 1/2, and delta 1 equals capital delta 1 over V1 to the 1/2, where lowercase delta 1 and delta 2 are cohesive energy densities or internal pressures as they are known sometimes, then RT natural log of F2 becomes V2 into delta 2 minus delta 1 all squared, Roman numeral 3. Let's look at an example. Let us consider an example of a reaction. Let's have a hypothetical reaction A plus B in an equilibrium reaction with an intermediate complex X, which then disintegrates to give you the products. Here, A and B react in the first step to form an activated complex. In the second step, then the complex then decomposes to give us products. We are interested in the rate of formation of products, and this is proportional to the concentration of X. Hence, the rate of the reaction will be given by rate is equal to K2 times the concentration of X, or in the old-fashioned way, K2CX. This is Roman numeral 1. No, not Roman numeral, normal 1. But the activation complex is in equilibrium with A and B. Therefore, we can say capital K, the equilibrium constant, is equal to AX over, in bracket, AA times AB, where A here is the activity. And in terms of concentration, this is equal to, open bracket, CX over CA times CB times FX over FA times FB. This is equation 2. On eliminating CX from the equation, because it represents the intermediate complex, which is very difficult to measure, from equation 1 and 2 above, we obtain, and we do this by substituting for CX using 2 in 1. The rate is then going to be equal to K naught FA FB over fx in bracket times Ca times Cb. Equation 3. Here K0 is equal to K2 times capital K. But we know very well that for a bimolecular reaction between A and B, we normally write the rate is equal to K experimental times Ca times Cb. Hence, the experimental rate constant, Ke, is given by K is equal to K0, Fa, Fb all over Fx. If we take the natural logs of these, we obtain natural log of Ke is equal to natural log of K0 plus natural log of Fa plus natural log of Fb minus natural log of Fx. Roman numeral 4. Here K is the rate constant in solution, and K0 is the rate constant in gaseous phase. Fa is the activity coefficient of reactant A, and Fb is that of reactant B. Fx is the activity coefficient of the intermediate complex X. But for a dilute solution, natural log of Fa is equal to Va over Rt times, open bracket, delta A minus delta B all squared. Consequently, natural log of Ke becomes equal to natural log of K0 plus Va over Rt delta A minus delta 1 squared plus Vb over Rt times delta B minus delta 1 squared minus Vx over Rt into delta X minus delta 1 squared. Roman numeral 5. So let's make some conclusions. Here, the cohesive energy densities or internal pressures depend on the nature of the compounds. If the nature of the compound is the same, then the internal pressures of the two compounds is the same. If the nature of A is same as the nature of the solvent 1 and that of B, this would imply that delta A minus delta 1 is equal to 0. Delta B minus delta 1 is also equal to 0. Consequently, natural log of Ke will be equal to natural log of K0 minus Vx over Rt times minus delta X minus delta 1 all squared. In conclusion, if the nature of the reactants is the same as that of the solvent, but that of the intermediate complex is not, the rate is smaller than the ideal value. If reactants are not similar to solvent, but the activated complex is, then delta A minus delta 1 is not equal to 0, and delta B minus delta 1 is also not equal to 0, but delta X minus delta 1 is equal to 0. Conclusions. Hence, natural log of K is equal to natural log of K0 plus Va over Rt times delta A minus delta 1 all in squared plus Vb over Rt times delta B minus delta 1 all squared. This implies that the rate constant will be larger than the one in the ideal solution. Generalization hints. If reactions produce products which are more polar than the reactants, polar solvents favor these reactions.